Welcome back to the deep dive. Today, we're going on a mission to radically reset your understanding of reality. Think about everything you experience visually. The blue of the sky, a red stop sign, the glow from your screen, that's all light. And yet, it is the most insignificant fraction of the energy that is constantly, and I mean constantly, surrounding you. We're talking about an infinite ocean of energy waves, and your eyes can only perceive one tiny, shimmering puddle within it.
That puddle is visible light.
Mm-hmm.
And today, we are charting the entire territory, doing a deep dive into the entirety of the electromagnetic spectrum, or the EMS.
So our mission is to take the sources you've provided and really pull out the clearest knowledge nuggets about this invisible universe. We're going to unpack these major bands: radio, microwave, infrared.
Visible, UV, X-ray, and gamma.
The whole lot. We want to understand what they are, how they were discovered, and why their unique energetic properties matter for everything.
For global communication, deep space astronomy, even your health. To start, I think we have to establish the fundamental physics underneath it all. All electromagnetic waves are, at their core, the same phenomenon. And they all travel at the same speed.
Speed of light.
The cosmic constant, yes. It binds them all together. But everything else changes. Their physical characteristics, their frequency, which we call F, their wavelength, lambda.
And the energy carried by each individual photon, E.
Right. And those three things are intrinsically linked. They're in this tight physical relationship.
So if one changes, the others have to adjust. You can't change one in isolation.
Precisely. You move from one end of the spectrum to the other just by adjusting the frequency. If you increase the frequency, the wavelength has to get shorter. And crucially, the energy of that individual photon goes up directly. So high frequency means short wavelength, which means high energy. And of course, the reverse is true.
What's truly, I think, hard to grasp is just the sheer scale we're dealing with.
It is. I mean, give us the scale. How wide is this spectrum, really?
The source material really emphasizes how massive this range is in the universe. In astronomy alone, just looking out at distant phenomena, the frequencies span from roughly 1 kilohertz.
And what does that mean in physical terms?
We're talking about waves that are thousands of kilometers long. They're found in the ionized interstellar medium, and they go all the way up to an astonishing 2.4 times 10 to the 23 hertz.
That number is almost meaningless in a normal conversation. It's just a huge number.
It is. And that number, that 2.4 times 10 to the 23, that corresponds to the energy of 1 GeV gamma rays, the kind of stuff that comes from nuclear and subatomic processes. The point is, the visible light we depend on, it's housed within a mere factor of 2, a frequency is somewhere in the vast middle of this unimaginable range.
And for most of human history, that tiny factor of 2 was everything we knew existed.
Yeah. It makes you wonder how we ever realized there was anything else. Anything beyond the rainbow. So let's trace that intellectual journey, the history of seeing the unseen. The story really begins, like so many science stories, with the Greeks. They studied reflection and refraction, but the formal idea of the spectrum, that orderly arrangement of colors, that really starts with Isaac Newton.
Right, in 1666, he used a prism to split white light. And he was the first to use the term spectrum. And he proved that the colors weren't some artifact created by the glass, but that they were intrinsic properties already there in the light itself.
Newton's work was profound, but it immediately brought this huge scientific debate back to the surface. Was light a wave, or was it a stream of particles?
And Newton was a huge advocate for the particle theory. On the other side, you had Christian Huygens, who was championing the wave description. Huygens could actually derive the laws of reflection and refraction with his wave model, but it was really Newton's fame that carried the particle idea forward for a century.
And the wave camp finally got its definitive proof in 1801. Thomas Young's two-slit experiment.
A classic.
It didn't just show light behaved like a wave. It created this interference pattern, which let scientists, for the very first time, calculate and measure the actual wavelength of light.
And that measurement is crucial. It provided the context for the huge intellectual leap that happened right around that same time. Science started thinking, okay, if light has a quantifiable wavelength, maybe there are other lights out there, other lights with wavelengths we just can't see.
And this breakthrough came incredibly fast. It was basically 2 men in 2 years.
So tell us about that discovery. Discovering invisible light. It sounds like pure scientific magic.
It was simple, elegant, experimental science. In 1800, you have William Herschel, a brilliant astronomer. He was studying the temperatures of different colors of sunlight. He used a prism, spread the light into its spectrum, and then he just placed thermometers in each color band.
Moving from violet to red.
Exactly. And he saw, as you'd expect, that the temperature increased as he moved toward the red end.
But the real insight came when he went beyond what his eyes could see.
Precisely. He moved a thermometer beyond the visible red end of the spectrum into a patch that looked completely dark, and he found the highest temperature reading of all. Herschel theorized these were calorific rays, heat rays, and they behaved like light but were invisible. We call that region infrared radiation. It was the first time the spectrum was extended.
Wow. So we found heat just lurking beyond the red, and the other side was found almost immediately after.
Yes. The very next year, 1801, a German chemist, Johann Ritter, was working at the opposite end, beyond violet. But instead of temperature, he was testing chemical reactions. He knew that light could cause silver chloride to decompose, to break down. And he found that beyond the violet end, these invisible rays caused the fastest decomposition, the fastest darkening of the silver chloride.
He called them chemical rays,
which we now know as ultraviolet radiation.
So within just 2 years, we doubled the known size of the light spectrum. One side found by feeling heat, the other by watching chemistry happen.
But the question was still there. What connected all of it? Visible colors, infrared heat, ultraviolet chemical rays. Was it all just a coincidence?
That unifying concept was still missing. And the key, as it turned out, came from linking light to electromagnetism.
The foundational work there was done by Michael Faraday.
Yes, in 1845, he observed what we now call the Faraday effect. He saw that when polarized light traveled through a transparent material, its polarization actually responded to a magnetic field. And that was the first concrete empirical evidence linking light directly to magnetism.
I want to just pause on that for a second. Light is affected by magnetism. That must have been the crucial clue for the mathematicians.
It was the intellectual detonator. It led to the defining moment of 19th century physics. In the 1860s, James Clerk Maxwell synthesized all known electrical and magnetic knowledge into four elegantly simple equations. These equations describe how electric and magnetic fields behave, how they interact, and how they propagate through space.
And what's so fascinating is that Maxwell's equations didn't just describe what was already known, they predicted something entirely new.
They did. They predicted that a change in an electric field creates a magnetic field. And a change in a magnetic field creates an electric field. This self-sustaining cycle, he realized, must propagate outwards as a wave.
So he analyzes the speed of this theoretical wave.
Right, using known physical constants. And when he calculated the speed, he found it matched the known speed of light almost exactly.
It wasn't just a startling coincidence, it was the realization that light is an electromagnetic wave.
Absolutely. Maxwell's conclusion was that his equations dictated an infinite range of frequencies of these waves, all traveling at sine. This was the first theoretical hint that this vast spectrum existed, stretching far, far beyond the IR and UV that Herschel and Ritter had found.
If Maxwell predicted this infinite range purely from math, how did the physics community react? Was it met with skepticism?
Oh, there was definitely skepticism.
Yeah.
Maxwell was a theoretician. The world needed experimental proof. Proof that these hypothetical low-frequency waves, the kind you couldn't detect with heat or chemistry, actually existed.
So Maxwell painted the picture, but Heinrich Hertz was the one who put the waves on the air.
In 1886, yes. Hertz built this simple but ingenious apparatus. He used oscillating charges in a spark gap to generate and detect these low-frequency waves, what we now call radio waves.
And he succeeded.
He did. And critically, he measured their wavelength, multiplied it by their frequency, and confirmed they traveled at the speed of light, c, just as Maxwell had predicted.
What stands out to me in the source material isn't just that he detected them, but that he showed these new waves behaved exactly like light.
He was incredibly thorough. He used these new radio waves to demonstrate reflection, refraction, even polarization. I mean, think about the engineering here.
Yeah.
The source notes that he actually focused the waves using a lens made of common tree resin.
Tree resin.
It just shows you how raw and practical the science was. He was using whatever was at hand to prove the fundamental laws of the universe.
That demonstration, using tree sap to manipulate radio waves, that paved the way for Marconi and all of wireless communication. And Hertz also managed to generate even shorter waves, what we now call microwaves.
So by the late 19th century, we had experimentally confirmed radio, microwave, infrared, visible, and ultraviolet. But the high-energy end of the spectrum was still unknown.
That changed dramatically in 1895 with Wilhelm Röntgen.
Röntgen was experimenting with cathode rays, so electron beams, inside a vacuum tube. And he noticed that when he turned on the current, a piece of fluorescent paper across the room started to glow, even though the tube was covered. He realized some highly penetrating unknown radiation was being emitted, so he labeled them X-rays, the unknown variable X.
And he quickly realized their immense power.
Almost instantly, he saw they could pass through soft tissue but were stopped by denser materials like berm, which led directly to the field of radiography.
And finally, the highest energy emissions, gamma rays.
Discovered in 1900 by Paul Villard, who was studying radiation from radium. At first, he thought they might be some kind of high-speed particle. Ernest Rutherford named them gamma rays in 1903, but it took until 1910 for William Henry Bragg to prove they were EM radiation, similar to X-rays but with even shorter wavelengths.
What an incredible journey, from a prism to thermometers to chemical reactions to pure math and then to high-voltage tubes and radioactive decay. But you mentioned the paradox earlier, the wave-particle duality. That old debate came roaring back.
It did, and it really complicated Maxwell's smooth classical wave theory. The problem came from the high-energy end. In 1901, Max Planck proposed that energy is not continuous, but comes in discrete bundles, or quanta. Then Albert Einstein solidified this in 1905, using the particle nature of light to explain the photoelectric effect.
So after the 19th century basically proved light was a wave, the 20th century said, well, actually, it's also a particle.
The modern position is that it's both, simultaneously. A duality that really depends on how you observe it. Whether you see it as a wave or a stream of photons is dictated by the interaction itself. It remains one of the most intellectually challenging concepts in physics today.
That history shows the spectrum is continuous. It's a smooth transition of frequencies. But even though the physics is continuous, the energy level changes everything, especially for biological safety.
That is the critical divide. It's not about the speed that's always c. It's purely about the energy carried by the individual photon and how that energy dictates its interaction with matter.
So let's isolate that distinction, ionizing versus non-ionizing radiation.
Ionizing radiation is the high-frequency, high-energy end, so gamma rays, X-rays, and extreme ultraviolet. These photons carry enough energy to ionize atoms. That means they have enough force to literally knock an electron completely out of its orbital shell.
And when an atom is ionized, what happens?
It creates a fundamentally unstable ion. This sudden, violent ejection of an electron causes chemical bonds to break. It leads to fundamental chemical changes and ultimately biological damage like DNA mutation. Ionizing radiation is structurally destructive.
Okay, so what about the other end, the non-ionizing part?
That includes visible light, infrared, microwaves, and radio waves. Their photons do not have enough energy to ionize atoms. They mostly interact by exciting electrons to higher energy levels, like with visible light, or by causing molecules to rotate and vibrate, which is what microwaves and IR do. They can still cause heating damage, of course, but they don't break apart the core atomic structure in the same way. The distinction is absolutely vital.
This division is incredibly important, and it brings us back to the main tool we use to study these interactions, spectroscopy.
Spectroscopy is, in essence, our extended eye on the universe. It's the tool we use to separate EM waves of different frequencies. We use prisms, diffraction gratings, specialized filters, and then we measure the intensity of the radiation at each frequency.
And it goes way beyond just splitting a rainbow.
Oh, absolutely. It provides a detailed fingerprint of matter. Atoms and molecules only absorb or emit energy at very specific frequencies. So when we observe light from a star or radiation absorbed by a chemical sample, those absorption or emission lines tell us exactly what elements or molecules are present.
So it's not just for looking at a rainbow, it's like analyzing the DNA of distant objects.
Precisely. For example, while the visible range is tiny 400 to 700 nanometers, common lab spectroscopes can detect wavelengths from 2 nanometers in the UV all the way up to 2,500 nanometers in the near-infrared. It just vastly expands our sensory window.
Can you give us a technical example of that in the non-visible range?
A classic one comes from radio astronomy. Neutral hydrogen atoms, which are all over the interstellar medium, they naturally emit a photon with a specific wavelength of 21.11 centimeters.
That's a very low-frequency radio wave.
Extremely low. But a radio spectroscope tuned to that frequency allows astronomers to map out the distribution and velocity of these hydrogen gas clouds across our galaxy and others, even though these clouds emit no visible light whatsoever.
It's incredible. That one specific low-energy wavelength can tell us so much about the structure of the cosmos.
And that concept holds true across the entire spectrum. Spectroscopy is how we translate raw energy data into verifiable scientific knowledge.
All right, let's begin our detailed tour of the spectrum. We'll start with the longest wavelength, the bottom of the energy scale, radio waves.
Radio waves have the lowest photon energy and the longest wavelengths. We're talking centimeters up to tens of thousands of kilometers. They're generated and received by antennas. The basic mechanism is you apply an alternating electric current to a conductor, which causes the electrons inside to oscillate. And those oscillating electrons create the radiating electric and magnetic fields that make up the radio wave.
And their application in our daily life is just unmatched.
They are the absolute backbone of modern communication. AM/FM radio, TV signals, mobile phones, satellite communication, Wi-Fi, Bluetooth.
And navigation systems like GPS, too, and radar.
All of it.
So what makes them so good for long-distance communication?
Their interaction with the atmosphere is key. For the most part, they pass right through foliage and most building materials. The atmosphere is mostly transparent to them. But certain frequencies can actually be reflected by the ionosphere, that layer of charged particles in the upper atmosphere.
The ionospheric reflection, how does that work in practice?
It's called skywave propagation. And it's why shortwave radio broadcasts can travel massive distances. You can literally bounce a signal halfway around the globe. WWII radio operators, for example, relied on this to skip signals over oceans and continents.
Moving up a bit in energy, we hit microwaves. What's the distinction here?
Microwaves are basically just short radio waves, wavelengths from about 10 centimeters down to 1 millimeter. They fall into the super high frequency, or SHF, and extremely high frequency, EHF bands. The move to higher frequencies gives you greater bandwidth and smaller antennas, but you need specialized gear to produce them, like magnetron tubes.
Okay, let's talk about the most famous application. Heating food. Why do microwaves heat things so differently from a conventional oven?
This is a beautiful example of molecular physics. Microwaves interact powerfully with polar molecules, and the most famous one is water. A water molecule is polar. It has a slight negative charge on its oxygen atom and slight positive charges on its hydrogen atoms. So when the oscillating electric field of a microwave passes by, it violently forces these polar water molecules to rapidly rotate to align with that shifting field.
So the heating is basically rotational friction.
Exactly. That friction generates heat. It's bulk heating. And because the waves are low energy enough, they can penetrate deep into materials and deposit that energy below the surface. Unlike, say, infrared, which is primarily absorbed at the surface. That's why a normal oven heats things from the outside in.
There's also a technical challenge with carrying these high-frequency waves.
Yes, absolutely. Traditional copper cables have massive power losses at microwave frequencies. So instead, engineers use these highly engineered metal pipes called waveguides to carry them efficiently. You see them in high-power radar systems, for example.
Before we move on, we have to talk about the terahertz gap. It was ignored for a long time, but it's a huge research area now.
The terahertz gap, or T-ray gap, sits between about 100 gigahertz and 30 terahertz. For decades, it was a gap because it was really hard to find efficient sources to generate energy in this range and also sensitive detectors to pick it up. But now, applications like high-speed wireless communications and advanced imaging are really emerging.
And some of those applications sound pretty futuristic, military uses.
They are. The source material notes that terahertz tech is being explored for directed energy, specifically to incapacitate electronic equipment. But the security applications are more prominent. Terahertz radiation is non-ionizing, so it's safer than X-rays, but it can pass through things like plastics, clothing, and cardboards.
So seeing through luggage or clothes at an airport?
Right. It creates an image based on the reflected signal. But there's a big problem. That strong absorption by atmospheric gases we mentioned earlier. Water vapor and other gases just soak up T-Hertz radiation. It simply won't travel far in humid air, which really limits its long-distance applications.
All right, from communications and heating, let's move up to infrared radiation, the energy we feel as heat.
Infrared covers a huge range, from 1 millimeter down to 750 nanometers. And it's divided into 3 parts based on fundamentally different molecular interactions.
Let's start with the longest, far infrared.
Far infrared is from 1 millimeter down to about 10 micrometers. This radiation is absorbed by the rotational modes of gas molecules, like water vapor, and this causes a big problem for astronomers. The water vapor in our atmosphere absorbs this energy so well that it makes the atmosphere almost entirely opaque in this range.
Which is why far IR telescopes have to be on high mountaintops, or even better, in space.
Exactly. Like the James Webb Space Telescope. They have to get above the atmosphere to see clearly.
Okay, next up is mid-infrared, the chemist's favorite tool, I hear.
Mid-infrared is from 10 down to 2.5 micrometers. This radiation is absorbed by molecular vibrations. A photon in this range hits a molecule and causes its internal bonds to stretch and bend and rock. And because the resulting absorption spectrum is unique to every single chemical compound, we call this the fingerprint region. It's the core of analytical chemistry.
And it's also the heat we radiate ourselves.
Yes. Human skin, at normal body temperature, radiates strongly in the lower end of this mid-infrared region, which is exactly why thermal imaging cameras can so easily detect body heat, even in total darkness.
And finally, near-infrared.
Near-infrared is the shortest IR, from 2500 down to 750 nanometers. The physics here is very similar to visible light. It involves electron transitions, but the energy is just a little too low for our eyes to see. Because of that, it can be detected by specialized film and standard image sensors, which is what enables night vision tech. It's also heavily used in optical fiber for telecommunications because certain near-IR frequencies travel very efficiently through glass.
Okay, we've crossed into the nanometer scale now and arrived at that tiny little slice of the spectrum our biology actually relies on, visible light.
It's a remarkably small window, isn't it?
Yeah.
Roughly 380 nanometers, which is violet, to about 760 nanometers, which is red. It's an interesting cosmic coincidence that the human eye evolved to be most sensitive right in this range, which also happens to be where our sun outputs its peak power.
How does visible light interact with matter differently from IR?
It's all about electrons moving between energy levels. Visible light photons have just enough energy to excite electrons to higher energy states within atoms and molecules. That specific action is what underpins human vision. The pigment cells in our eyes react to it, and it also drives photosynthesis in plants.
And the colors we see are just the frequencies that bounce back to us.
Exactly. A banana looks yellow because its molecules absorb the blue and green frequencies and reflect the yellow ones into your eye. Your brain does the rest. Outside of this very narrow window, pretty much all the information we gather requires a technological sensor.
And stepping just beyond violet, we hit ultraviolet, or UV, radiation, and this is where we cross that critical dividing line into ionizing radiation.
That is the crucial designation for UV. It ranges from about 399 nanometers down to 10. And it has enough energy to start knocking electrons off of atoms.
UV seems to have this fascinating duality. It's a useful tool, but also a major threat.
It really does. On the useful side, UV causes many substances to glow with visible light, which is a process called fluorescence. This is used in forensics to find biological fluids, and it's used in security. You know, the little things on money or your ID that glow under a black light.
Right.
That's UV at work.
But the downside is the biological damage. The reason we all wear sunscreen.
That damage is primarily caused by the middle range, UVB. It has enough energy to break chemical bonds inside your DNA. It specifically creates something called thymine dimers, which is where it sort of welds two bits of your DNA together. This makes UVB a potent mutagen and the main cause of sunburn and most skin cancers.
And our atmosphere is what shields us from the worst of it.
It's absolutely critical. The most energetic UV, vacuum UV, is completely absorbed by nitrogen and oxygen high up. Then, most of the dangerous UVB is blocked by the ozone layer. What mostly gets through is UVA. It's less damaging than UVB, but it penetrates deeper into the skin and still contributes to mutations and aging over time.
Moving higher in energy, we hit X-rays.
X-rays are the next step up in ionizing power. They interact by ejecting core atomic electrons, the ones deep inside an atom. And at these energies, they also interact via something called the Compton effect.
Can you explain that simply for us?
Think of it like a game of billiards with light. The X-ray photon, the cue ball, strikes an electron. It transfers some of its energy to the electron, and both of them scatter off at different angles. This allows the energy to get deep into matter instead of just being absorbed at the surface. That's what gives X-rays their penetrating power.
Which is why they revolutionized medicine.
Precisely. Diagnostic imaging, radiography, it's all based on the fact that dense things like bone absorb more X-rays than soft tissue, creating a shadow image. But they're also vital in astrophysics for studying things like accretion disks around black holes and the super-hot coronas of stars.
But just like with some of the other bands, our atmosphere gets in the way.
It's a total barrier. Our atmosphere is so dense to X-rays, it's like trying to see through 10 meters of water. So virtually no astronomical X-rays reach the ground. X-ray telescopes have to be in space.
And finally, we arrive at the top of the ladder, gamma rays.
The most energetic photons of all. And here, the distinction from X-rays isn't just about energy, it's about their source.
What's the source difference?
X-rays are generated by electron transitions, electrons moving around in an atom. Gamma rays, on the other hand, are generated from nuclear decay or other subnuclear processes. They come from the nucleus itself. If it's from the nucleus, it's a gamma ray.
And what does that extreme energy do when it hits matter?
The interaction is violent and deeply penetrating. It causes widespread Compton scattering, the ejection of core electrons. It can even excite and break apart atomic nuclei. At the very highest energies, gamma rays can cause something called pair production, where the photon's energy literally converts into mass. It creates an electron and its antimatter counterpart, a positron.
Energy converting directly into matter. That really drives home the power level.
It does. But despite that power, we use them. They're used to irradiate food for sterilization. In medicine, they're used for radiation cancer therapy and in diagnostic imaging like PE scans.
And like X-rays, to study the cosmic sources, you have to go to space.
Absolutely. The atmosphere blocks them completely. Gamma-ray burst observatories are essential for studying the most energetic events in the universe, but they have to operate outside our protective atmospheric shield.
So we've completed our journey across the electromagnetic spectrum, from kilometer-long radio waves up to the atomic-level power of gamma rays.
And what we've really seen is that the spectrum is a continuous flow. The distinct names we use are just practical labels. They're driven by the huge difference in how the energy in each band interacts with matter, whether it rotates molecules, excites electrons, or completely shatters nuclei.
And that interaction is dynamic across cosmic distances. What an object emits isn't always what an observer sees.
Right. We have to think about things like the Doppler shift. If a star is moving away from us, its light shifts toward the red end of the spectrum. It gets redshifted. But on the grandest scale, we deal with cosmological redshift.
Which brings us to the oldest light we can detect, the cosmic microwave background.
That's right. That relic radiation from the earliest universe was originally emitted when the universe was incredibly hot and dense. Its energy was around 1 electron volt, which would put it in the near-visible light region.
So it started out as bright light.
It did. But over the last 13 billion years, the expansion of the universe has stretched the fabric of space itself, and it has stretched those waves along with it.
Stretching them all the way from visible light down to the microwave band where we see them today.
It is an incredible transformation. So here's a final provocative thought for you, the listener, to explore. If the cosmic microwave background started as bright, visible light and has been redshifted so much that we now see it as low-energy microwaves, what other truly powerful, unseen astrophysical events, maybe the very first stars or massive galactic collisions, are having their visible or even their X-ray radiation redshifted so profoundly that we currently only detect them as faint signals deep in the longest radio bands, just waiting for the next generation of antennas to discover them? The invisible universe may hold secrets far larger than anything we currently observe.
A truly inspiring thought to end on. Thank you for joining us for this deep dive into the invisible spectrum of reality. We'll see you next time.